These technique can also be used on Mars and in other places in the solar system. And what we're going to do is we're going to go and we're going to take the sample of the soil and we're going to heat it up to 900 degrees Celsius and we're going to flow hydrogen over top of the soil. And that will actually, through a process called hydrogen reduction, extract the oxygen off of the ilmenite. It will attach to the hydrogen and form water. So we can actually make water with only taking hydrogen. The reason you want to do that, hydrogen is so much lighter and it's so much easier to take that resource. And so mass is such a huge expense for launching that this allows you to launch a small robotic mission that could actually make water. The water can be used as potable water, or it could be broken down into hydrogen and oxygen, which can be used for fuel or breathing oxygen. So you can make a lot of the resources that you need for human exploration. So that's the ISRU, the in situ resource utilization part of it. We also are going to be determining what other volatiles are there, including water. And so in order to do that, we have an entire instrument suite. This was the demonstration we did out in Hawaii in Mauna Kea. We were at 9,000 foot, and that simulates the regolith, or the tephra, what they call the dirt there is tephra. That simulates the lunar regolith very well. It has very similar geotechnical properties, and it also gives us a very good chance to remotely operate. You can see we had this is an exact example. This is one of our comm guys here. We were operating in a field through a missions operations center that was on the other side of a mountain. So we were not able to cheat. We weren't able to look out and drive the rover by stick. We fully teleoperated this to do a full mission simulation. Some of the instruments that we had on there, we start with a neutron spectrometer, and essentially that acts like a metal detector. You're roving around the lunar surface, and you're looking for a signal, a drop in neutrons, which indicates the presence of hydrogen. You then would take your auger, and you could auger down in the ground, and as the soil comes up, you can look with a near-infrared spectrometer and determine what is that source of hydrogen. Is it hydroxyl? Is it water? Is it a hydrated mineral? And so from there, you can say, okay, well, this is a really good sample. I found water. Let me go ahead and take this push tube on the drill, acquire the sample, and then it goes into what we call the oxygen volatile extraction node, oven, fancy term. And the oven is just that. It's a reactor that can heat the sample up to 150 to 300 degrees Celsius to drive all the water off. The water then goes to the lava system. I'm going to let Mary Cohen talk about the lava system.
So the lava system is basically just a fluid subsystem. It takes the gases from oven and it will transport them to the end result, which is out into the moon's vacuum or the vacuum of space. So the idea is we'll take the gases that come off the oven and we'll put them in a surge tank. In that surge tank, we'll be able to sample the gases and determine what's in them using what's something called this GCMS, or gas chromatograph mass spectrometer. Using that, we'll be able to determine the quantities of water, the quantities of hydrofluoric acid, for example, or other just hydrogen. From there, we will then transfer it to a water drop demo, which you see here. This is a prototype that we have. And here we will actually impinge the surface of a cold finger on the back. It's the metal piece right there. And it will condense the water onto the surface. We will have a camera right there, so you can actually take a picture of the water condensing to show the people on Earth that there is actual water that comes out of the regolith. From there, it will then be expelled out into the space, away from any other instruments or any type of soil where we could potentially, contaminate the surface.
One of the big things our project manager always likes to talk about is that in previous missions we've shown water presence on the moon as a single line on a spectrograph, which doesn't necessarily capture the public's attention. But if we can actually take a physical image of a water droplet that we captured from the lunar soil, we really feel like that is a much more of a eureka moment for the public, and that's really what the focus of the water droplet demo is. A couple other things we wanted to point out is that we're actually partnering with the Canadian Space Agency. They're providing the rover and the drill that just disappeared. And the drill. So we have a partnership with the Canadian Space Agency, and we're also partnered with 5 NASA centers in total. So 2 of the instruments that I've mentioned already, the near-infrared spectrometer and the neutron spectrometer, are both coming out of the Ames Research Center. The oven is coming out of Johnson Space Flight Center. Our thermal lead is out of Johnson Space Flight Center. Our software, avionics, and our lava team is here at John Kennedy. We also have power distribution done by Glenn Research Center. And for the flight mission, we're hoping to be approved for flight in the next year or so. And the flight mission will utilize a lander team that is led up out of Marshall Space Flight Center with support from Johnson Space Flight Center as well. So it really uses the expertise all over the country that NASA possesses, as well as international partners in the Canadian Space Agency. Are there any questions anybody has? I can keep talking. So.
Well, do you guys want to know about more of the history side? It's not like we just started off there.
That wasn't our first attempt. It took a couple years to get there.
Yeah.
So Mary, if you want to talk about the EBU too.
Sure. This is the second prototype. The first one is EBU1. This is EBU2, or Engineering Breadboard Unit 2. Sorry. And then from here we went to FDU, which you see up there and in the video. That's Field Demonstration Unit. And now we're working on ETU, which is the Engineering Test Unit. That's the next step before we build our flight unit. Here we can see how there's pretty much the size differences here. Here we have the oven in the back where the soil would come in, go into the reactor and heat up. From there we have fluid lines that lead to the lava subsystem in this case, which is this big box right here. And this piece here is the GCMS, or actually just the GC in this case. We just had a gas chromatograph. And from here, we've shrunk this down significantly. You can't see it on there because it's in a big box. But for the ETU unit, we've gone from this down to probably about that high if you count everything together. So it is a significant reduction in mass, time, and money. So really, it's a great significance, especially for the GC. And we're actually adding a mass spectrometer, which is a new technology that will go to the moon.
Yeah, the mass spectrometer was a technology that was developed at a Jet Propulsion Laboratory, which is another NASA center that's actually, I've failed to mention, but they are partnering up to take what they took at technology, they commercialized it for the commercial industry, and people are always looking at how NASA technology is commercialized. This was commercialized to a company that was able to use a desktop mass spectrometer for labs. And then we're now taking it back and saying, okay, well now we want to make it spaceflight qualified. So we're taking it, we're going through the rigors of making sure it's vacuum compatible, making sure it can survive the environment of launch. So it's kind of we've gone full circle. We took a technology, we developed it, we commercialized it, and now we're working with a commercial partner to actually make it spaceflight qualified.
So how is the mass spectrometer on this going to be different from the one on the Curiosity? Is it like the same basic technology? Or is it
it's similar. The Curiosity mass spectrometer, if you're referring to the same instrument suite, was a quadrupole mass spectrometer. Fancy words. The biggest difference is takes time in order to get your mass range. Okay. You sweep your energies so that you have a single detector, and when a particle hits that detector is its mass. The technology that's been developed at JPL is like a CCD camera with multiple cells, and as you accelerate all the particles at once and where it hits. So you can do your entire sweep in about a minute to 3 minutes.
It's actually less than that. The GC is what actually takes most of the time, but yes, it's very quick.
Yeah, so and which is really nice because if you look at future technologies, it's like entry probes. When you do an entry probe, we recently did an entry probe, Cassini-Huygens went into the Titan, and you have an hour and a half or a 2-hour descent. Well, if it takes a half hour to do one sweep, you can't get as much statistical significance if you've only got 3 or 4 runs. With this, you'd be able to get hundreds of runs. So it is a big advancement.
And I did forget to mention that on the ETU unit, we have a near-infrared spectrometer actually attached to our surge tank as well. So we'll be able to get the signals off that water, how much water is present in our surge tank before we even send it to the GCMS.
And this will be a mag. If you know much about mass spectrometers, this is a mag sector mass spectrometer where the MSL used a quadrupole mass spectrometer in the SAM instrument suite. So it just a different way to accelerate the ions.
Very glad I'm recording this.
Hopefully I didn't misspeak too much. I was involved with SAM instrument suite up at Goddard, so I have a little bit of insight into that, but I did not work on the GCMS itself. So. Additionally, that had 6 gas columns. We're going to be having 1 gas column for this mission. They were looking at much wider range of molecules that they were trying to separate out than we expect to see on the lunar surface. Also, isotope detection is something we can do.
Yes, we can do isotope detection on our unit as well. And we can separate, because with water out, if you know much about GCMSs, they don't really like water. In fact, most GCs, the companies will actually make them so there is no water in it. They don't want water in their system, and they try to get rid of it. We're actually purposely putting it into it, so that has a lot of challenges involved. So there are a lot of issues that we work in-house and with small business companies in the United States that are helping us with this issue.
Yep. And isotope detection will actually let us determine how the water got to the moon in the first place. Was it delivered by a comet? Is it solar wind that basically the solar wind can then impinge the lunar surface and migrate to the hydrogen can migrate to the cold traps and bond with oxygen. So it helps us determine the emplacement as well. So there's quite a lot of science that the lunar community is excited about, as well as the ISRU community.
And then this also leads to the Mars. That's what I was saying at the beginning. It really lets us,
the ISRU allows you to expand human exploration throughout the solar system. So. All right, Paul, do you want to talk your gas to trash? Another ISRU technology.
So I'm going to come over here.
Paul Hansen.
Yeah, my name is Paul Hensey. This project is the goal of this overall goal of this project is to have to reduce the logistical mass that we have to send in space. It costs a lot of money to send anything into space. So anything you send, you want to make sure you use it. You don't want to have to throw it away. So some of the tasks that we're doing in there is we're trying to make clothing that lasts longer on astronauts so they don't have to throw it out. Another one is just to reuse things that are sent up. And then the final two technologies, what I'm going to talk to you about here, this deals with the trash that's generated during spaceflight. So just like in your house, you generate a lot of trash. You've got food waste. This is an example of the food packaging. So it's a polymer packaging with some aluminum. It's the shrimp cocktail. So you end up with this is a delicacy. You end up with a lot of this just plastic waste and leftover food in addition to clothing. That is, what are you going to do with this? So right now it ends up getting stored, so it's a volume issue. So they stuff it off in some place. You can't use that spot. It might smell because it's leftover food. So, you know, what do you want to do? You want to get rid of it. B, you want to make something useful from it. So what we do with this technology, and we're implementing a new reactor that we haven't run yet. We use technologies called gasification or pyrolysis or incineration, and we want to convert the trash into something useful. So our goal really right now is to produce methane, which can be used as a rocket fuel. So we burn the trash, we take it to a second reactor, a Sabatier reactor, and that can convert the CO2 into methane that can be used for rocket fuel. Another thing that we can also do, and this is being done here as well as at Ames, you can take the trash and put it in the trash compactor, and you make what basically just a tile from the trash. So you can see the bags. This is a food packaging bag, and this is actual shuttle trash. This stuff can be used as radiation shielding. So while you're in space, you can produce the radiation shield to protect you from events when you're out there for a long period of time. So we've got two things. We're trying to make rocket fuel, radiation shielding, and this can also do things like make water that can then go back into the life support system. So really we're taking what is considered a problem and trying to make it into something useful. We want trash to be a resource in space. We want to use it all, reuse it, get something good out of it. Any questions? Sure.
So can you walk us through this really quickly?
Okay. This is it's modeled after what's called a downdraft gasifier. This is a technology that's been around on Earth for a little while, actually for quite a while. You put the trash in on the top, you heat the top of the reactor, and the white things are heaters. Air flows in through the bottom. It oxidizes the trash as it gets hot, and you end up with a gas stream that comes out. That gas stream, depending on how you're running, you can actually take that to a generator and produce electricity directly, or you can go into something else that produces methane. When it comes out, we have a condenser that collects the water, so this would be, could be reused for life support, or it could be electrolyzed for oxygen and anything else, and then the outlet, goes to whatever kind of processing we're doing. We think of this as a multi-mission technology, so if somebody wants to use methane, so methane fits in on a Mars mission because ISRU process can turn the atmosphere into methane, so this would be an additional methane resource. Under other circumstances, people may be more interested in just getting the water out. So this polymer contains hydrogen and oxygen atoms in it. That's not water, but once you run it through the reactor, you can recombine them and do water that way. Terrestrial applications, right now, there's not too many of them, but there are places that take landfill waste and they make electricity. And it's a technology very much like this. It's just on a much bigger scale, and they may operate at higher temperatures and pressures than would be desirable for us. And one of the very first applications of this was in World War II during gas shortages. They were able to take wood chips, gasify the wood chips, and that product gas can be fed directly into an internal combustion engine so they could drive the cars off wood chips. And you can still do that today. So we're doing exactly that. Trash comes in, power comes out, you can fly your spacecraft. Anything else?
Thanks, Paul.
All right. Thank you.